Hello and welcome everybody to this tutorial on signals and threads. We're going to be looking at how signals interact with threads and what we can do with that. So basically in Linux, signals are can be seen kind of like interrupts. So you can send a signal to an application and your signal handler will run. Basically the application will be interrupted and your signal handler will run. And then when your signal handler exits, then the application will continue. But what actually happens, like how can we actually synchronize the signal with threads? Like we cannot use mutexes because they're not designed for that kind of thing. They're not designed for something that arrives asynchronously. So what we have to do is use pthread. Let's see here. What we have to do is use pthread signal mask sig mask to mask out the signal that modifies some data that we want to modify, and then we can re-enable the signal, and the signal can then modify the data without us having to worry that that we will be modifying some data that the signal is also modifying asynchronously. So this is a way to ensure integrity of the data. And it works pretty much the same as enabling and disabling interrupts on a microcontroller. So if you've been programming microcontrollers, you're familiar with this. But if you haven't been programming microcontrollers, then this is probably something new for you. So let's look at some code. We're going to use a key to bind thread-specific data. And we're going to have a data structure for our thread data. And then I also use sigatomic here, which is a variable that I'm going to be accessing from both the signal and the application. And I use volatile because I want to disable optimizations. Volatile is really nothing special. It's just a keyword that disables optimization, so the compiler will not put values. It will not rearrange operations when it comes to modifying or reading and writing this variable. And so if you're interrupted by a signal, you know that the variable, whenever you access that variable again, it might have changed, right? So there wouldn't be any kind of optimization that says, oh, I'm going to load this variable into register and I'm going to just reuse the register. Instead, the compiler will actually load the memory location of that variable to make sure that we always have the latest value. And sigatomic is basically defined as int, but the key here is that it's any data type that you can read and write using a single instruction on your processor. So for example, if we have long, then this can take 2 instructions, and if you're interrupted in the middle, you're going to get inconsistent data. What sigatomic guarantees is that you always get either the old value or the new value, and never something in between. Let me just also do like this so that we have our canvas properly configured here. So next we go to signal action, and when you register a signal handler in a Linux program, it's always a global signal handler. It's not a per thread signal handler or anything like that. It's always a global signal handler. So it naturally doesn't take any parameter that signifies data, because it just doesn't make any sense, right? Because this signal handler will basically execute at any time when we execute in some code, and then suddenly the signal occurs and it will call this signal handler, and then the signal handler will run. And it can also be another thread, and then that will run, or it can be the main application, and then that will run as well. So we have no way of really passing any data to this handler, but what we can do is register a thread-specific variable using this global key that I've defined here, or that I've defined further up here. And using that key, we can retrieve the thread data structure for the thread that has been interrupted. And for the sake of this example, I can I'm going to use just that, and I'm also going to check here if this data structure is set, because if we get a signal sent from outside of the application, because for example you can use the kill command on the terminal, and then you can use the S option, and you can send the user1 signal to your process, and if you do that, then your main process will receive the signal and not your particular thread, and so this will be null because you haven't set this specific for your main process. And so the only thing I do here is I print that interrupt has occurred. You shouldn't use printf in signals. Not a good idea, but for the sake of just showing what happens, I just print some text here. And I also check if we are in the critical section, and if we are, we print an error on the console. And then in my thread function, then the only thing I can do there is I can block signals, and I can unblock signals. So I create this signal set here, and I add, using this function called sig add set, I add my user1 signal, which I'm going to be using to interrupt the process. And I then block this, I call pthread sigmask to block this signal while I'm manipulating the critical variable. And when I'm done with that, I unblock the signal. So what we have here then is that whatever structure this happens to be when the signal occurs, it's always going to be belonging to some thread, and if that thread has blocked the signal, then this will never belong to that thread, because the signal handler will not execute until that signal is unblocked again. So this is how we can make sure that we don't get inconsistent data, and so that we don't try to access this data at the same time. But if we comment this out, we'll get the error in this that is printed out here. So then it's basic thread creation, and then I register the sig action here in the main application. And first of all, I also create the key. So the key has to be a global variable, and it has to be accessible by all threads. So we have to initialize it using pthread key create. And then I create the threads, and each thread then sets this key using set specific here, and it sets it to itself, to the pointer to its data structure. And for the thread function, we can pass the data through a pointer, which pthread will pass to our thread routine. And then I just then I sleep for 1 second. This is just to make sure that the threads have started. I should normally use a semaphore that I wait for to make sure that threads have started. But here I just put a sleep to do it quickly, and then I have I call pthread kill to deliver the signal. So you can use pthread kill to deliver a signal, just like you use the kill command on the terminal to deliver a signal to a process. You can use pthread kill to deliver a signal to a thread. And then this just loops around, and we basically see text that it gets printed out on the console. Let's have a look at the console. Let's see. So if we run this application now, we basically get interrupted sometimes on thread number 1, sometimes thread number 2. And so it goes. And if we disable this, what basically happens is that we will get the concurrency stuff. So it's really simple. So now we are interrupting in a critical section. So very simple, very straightforward, but good to remember. And I hope you learned something. I'll see you in the next video.